I'm back, and I had promised you last time that we shall discuss subgroups of SO3. So what are all subgroups of SO3? When I say SO3, I mean SO3R, which is also group of rotations in R3. And I had emphasized it towards the end of last lecture that all platonic solids can be inscribed in a sphere. Everything is perfectly symmetric, so I can perfectly put them inside sphere. All of them, I can put them inside the sphere. Yeah. So if I put them inside sphere and I do all the operations which are symmetric for these objects, I am actually rotating the sphere. That is, I am considering therefore these symmetric operations of these objects as elements of SO3. So that's easy. Therefore, conclusion is that all those elements which were groups of rotations of tetrahedron, you remember what it was? It was A4. Rotations of cube, that was A5. Rotations of dodecahedron or icosahedron, that was, sorry, here rotations of cube is S4 and rotations of dodecahedron A5. So from the observation that all platonic solids can be inscribed in sphere, what we conclude is that all these are subgroups of SO3. And we had also observed last time that cyclic groups, which are anyway subgroups of SO2, are also subgroups of SO3, say finite cyclic groups if you wish, finite cyclic groups. So certainly if you want to list finite subgroups of SO3, you will have to have A4, A5, S4 and all cyclic groups. But the question is, what are all finite subgroups of SO3? So these are certainly few, but what about others? And that's where the fun part is going to be, and we are ready with group action. So it's a good application of group actions. Let me read out the theorem for you. If you have a finite subgroups of SO3, then following are the options for it. Nothing else can be finite subgroup of SO3. It could be finite cyclic group, finite dihedral group, Klein's 4 group, or these three things which are coming from platonic solids. And this we have already observed, this also we have observed. So this we have to observe today. But more than that, we are supposed to show that if you pick any finite subgroup of SO3, then that subgroup is one of them. There is no other. So nothing which is not there in this list is going to be a finite subgroup of SO3. So that's quite amazing. So as I mentioned, Cn appears because of SO2, and let's see why Dn should appear. And Dn appears because all regular polygons, the two-dimensional ones, all regular polygons can be inscribed in a sphere. That's correct. You have a sphere, you consider the equator of the sphere, that is circle, and on that circle you can have all regular polygons. So if you have regular n-gon, what you have is dihedral group, right? Because you can have, just imagine as if this is circle, when I move I get cyclic group, and when I rotate it along some axis on the sphere, what am I doing is actually I am flipping the plane of the equator. So rotating in 3 dimensions like this, that is swapping north and south pole via rotation, is actually same as flipping of the regular n-gon which is there on the equator. So that's how you get the group Dn. So Dn is fine. What about Klein's 4 group? How do we imagine Klein's 4 group? We are going to see after a few slides. But remember, the purpose is we shall start with arbitrary finite group which is a subgroup of SO3, and then we shall show that it has to be one of these which is there in the list. Okay. So for this theorem I am going to have proof. So I have to start with arbitrary finite subgroup of SO3. So I start with a finite subgroup of SO3. Now what is there to start with? Well, we can have what are called poles. We can have poles of rotation. So what is that? I'll just take one of these objects. Say I take this, and I imagine that I have inscribed it inside a sphere. So these vertices will be touching the sphere, right? Faces will be slightly away from them, only the vertices will be touching the sphere. That's what is the meaning of inscribed. So all those points where these vertices are touching, they are potential axes for symmetry, right? I just hold these vertices and I just rotate. So points which are touching the sphere, these vertices, so opposite vertices are forming potential axis for a symmetry operation, and these things are going to be called poles. Something more, I can have rotation through an axis which is the opposite sides, opposite faces, right? So if you just extend them to touch the sphere, similarly you extend the bottom to touch the sphere, then the point where it touches the sphere is again going to be called a pole, and similarly for edges. So all these things are going to be poles for this object. So I start with some consideration on poles. So what I have been given is just arbitrary finite subgroup of SO3 which a priori has no geometry. So I can't really express the poles in terms of what I did, but I will do it in some other terms. One thing is very clear, each element of G is a rotation, it's an element of SO3. So since every element is a rotation, there is an axis. Every rotation has an axis of rotation. So I denote by LG the axis of rotation, and then I intersect axis of rotation with S2. S2 is a sphere. So what do I get? That's how I get poles. So LG, just take it to be infinite line, infinite length line. So all the axis all the way is going to intersect with S2, and those 2 points where it's intersecting with S2 is those points are going to be called poles. So here's the definition: elements of X, you call them poles. and LG intersection S2, these are two elements. The two elements in this intersection, one just say north pole, other just say south pole. So they are called poles of G, poles for that particular axis. And it's clear that since G is finite, for each G you have one LG, so there are finitely many poles. Number of poles is finite. And if G is a cyclic group, then there are only two antipodal points in a pole, right? Because when you have some cyclic group, again I am taking this cyclic, just imagine as if it's a sphere, when I am having cyclic group, there is only one pole, there is only one axis. Cyclic group meaning there is only one axis. Therefore, X will have only two elements, just the antipodal points. Now, what is the idea of the proof? Remember, we are proving that there are finitely many possibilities for subgroups of SO3. We have defined these poles. We shall do some jugglery with those poles. We shall make some observations about how those poles are distributed all across the sphere, and depending on our observations of the distribution of poles all across the sphere, we are going to make predictions about what G could be. In fact, that distribution would completely be determining what our group is. Okay, so here is the first observation. First observation is that one can give a very nice action of G on X. So whatever G we started with, it actually acts on set of poles of it, poles of G, which, and the set of poles is being denoted by X. It's easy to see, let's see. So I take some element which is a pole, and pole for some axis for some H. So H is eventually an element of SO3, and for that SO3 element H I have axis and then I have pole. So what is clear is that H, this rotation does not move this pole. That's correct. If I am rotating like this, then north pole and south poles, they don't move. So HP is P. And now if I take any arbitrary element G in G, then I make this calculation, G at G inverse acting on GP. GP is what happens to this pole under the influence of G. So G at G inverse GP is simply GHP, which is GHP. HP is not moving P because H is precisely the rotation for which P is pole. So I have this to be GP. So what is happening? Therefore, G at G inverse GP is GP. That means there is some element in G which is not able to move GP. That means this element GP is fixed by G at G inverse, and therefore it is fixed under the influence of some element, some rotation, because every element of G is a rotation eventually. So therefore GP is also a pole, and for this pole the axis is L G H G inverse. So that particular axis is having GP as a pole. So what we have concluded, if P is a pole, then GP is also a pole. What is the action? It is just simply that G as a rotation is trying to move P. That is the rotation. So GP is influence of rotation determined by P on, sorry, determined by G on P. So that's an action. G acts on poles. Okay, and as I said, we are going to investigate distribution of poles and what are the orbits of that action. All that is what we are going to analyze. So we start with, you remember Burnside's formula? In very beginning I had mentioned Burnside's formula. What it is? Number of orbits is equal to average number of fixed points. So this is number of orbit for this action. So number of orbits for the action in question is this, and why this is there? So for identity is going to fix all the poles. How many poles are there? Size of the set X. X is precisely the set of poles. And what is this? Rest of the mod G minus 1 non-identity points. They are fixing only two poles which are on the axis, which are the two sides of two edges of the two nodes of the axis. So those are mod G minus 1. So this mod X is precisely size of fixed points of identity, and for non-identity, so if G is different from identity, then fixed points are going to be only 2, right? So that's how I get this. Again and again, quite frequently I am going to use this formula. Now I am just writing this in slightly different way. So for each orbit I choose representatives x1, x2, xn. So from each orbit I am picking one element and then I rewrite the summation in this form. So everything is fine here. The only thing is, in place of x I am just writing this. So for each, so I am having for each orbit one element, and that element is contributing how much? Equal to the size of its orbit. So this is precisely the count of all orbits, and union of all orbits is precisely your set on which the group is acting. So you have this, and in fact some manipulations I would do with this. So I take this to the other side and divide by G. So what I get are these quantities. So this is n minus 1 by summation G, summation of all the orbits, and here I write orbit xi and take mod G inside, and you remember orbit stabilizer formula. So orbit of an element divided by orbit of G is 1 divided by stabilizer of xi, because orbit into stabilizer, size of orbit times size of stabilizer equals size of the group. So what we get after all these manipulations is that 2 times 1 minus 1 divided by order of group is equal to 1 minus 1 divided by size of stabilizers, and take the summation. So this formula again I am going to use multiple times, this also I am going to use multiple times. If group is non-trivial, that is group size is more than greater than equal to 2. So I have this because group is non-trivial. So here I have 1 by n, where n is greater than equal to 2. So this number is certainly more than 1, and since this is less than 1, twice of something less than 1 is less than 2. So this is what I have, and this expression 2 times 1 minus 1 by G from this is summation of 1 minus 1 divided by size of stabilizers. So just that much I replace here. So 1 by 2 here, 2 here. So I get this expression, and now I am taking summation over all orbits. So this is a constant half, number of orbits is n, constant 1, number of orbits is n, and here the summation is happening, right? So what I have is n by 2 is less than or equal to twice of this, because this is precisely, the summation is precisely twice of 1 minus 1 divided by size of g. So I get this expression. So n by 2 is less than or equal to this is what I get, and this expression is anyway less than 2. So when I combine this, this is strictly less than 2, and therefore n, which is number of orbits, is strictly less than 4. And also my group has size greater than or equal to 2. So when I take that into consideration and look at this, when I look at this, what I get is half is less than 1 minus 1 divided by mod g less than n by 2. So again, this is going to be quite useful for me. So from this, what I conclude is that n is greater than 1. So n is greater than 1 and n is less than 4. That means there are only two possibilities. That whenever group, a finite subgroup of SO3 acts on its poles, number of orbits is either 2 or 3. That's quite substantial information, and from this information we are going to get all possible subgroups of SO3, and in fact we are going to show that they essentially come from platonic solids or polygons, which is the case of SO2. So case by case analysis, first we do for n is equal to 2 case, and then we do analysis for n is equal to 3 case. So n is equal to 2 case. There are only 2 orbits. So if n is equal to 2, then size of x is 2. Why is that? Let's go back and look at this. So if n is 2, then 1 divided by size of g times mod x plus size of g minus 1 times 2. So what happens here? In order to get 2 here, so just let me just get mod g that side. So twice of size of g is therefore size of x plus twice of size of g minus 2. So this cancels out and you get size of x is 2. So size of x is 2 if n is 2. So number of poles is only 2, and if there are only 2 poles, they have to be antipodal. So they have to be antipodal, and both of them are in different orbits because number of orbits is 2. So I cannot move this pole to that pole, right? So what is the picture now? Like these are actually antipodal. I cannot move this from that, and this is happening when x1, x2, the line joining those 2 poles is actually the axis, and now your group is moving and this is rigid. So the only possibility is your group is cyclic. So all cyclic groups occur as subgroup of SO3, and n is equal to 2 possibility is that one. That was quite straightforward. N is equal to 2 is precisely cyclic groups. So now n is equal to 3 case is something which is interesting. So can you imagine what n is equal to 3 would be corresponding to when you think of platonic solids like this, say like this? There are 3 types of poles. Poles which are coming from vertices, poles which are coming from edges, and poles which are coming from midpoints of faces. And pole which is coming from midpoint of faces cannot go to it cannot go to the pole which is on the midpoint of edge or a vertex. That's the interpretation. So this 3 stands for edges, faces and vertices. Axis determined by them. Axis determined by them. And for that matter, every vertex is as good as any other vertex. As good as in what sense? They are in the same orbit. Similarly, any midpoint of edge is as good as any other because they are in the same orbit. By certain rotation, by certain action of the group of symmetry of this, you can obtain one from the other. Okay. So n is 3. So what we do? We take representatives from these 3 orbits and we are calling them earlier x1, x2, x3, xn. Let's simply call them x, y, z. And one of the formulas that we had earlier, remember what formula it was? Summation of stabilizers. This formula which says that twice of 1 minus 1 by this is summation of stabilizers. So using that you conclude this thing, that 1 is less than 1 plus 2 divided by g is precisely sum of reciprocals of sizes of stabilizers. Now here comes an observation. How large could these be? How large could these be? If all of them are greater than 1 by 3, then this quantity will be less than 1. But here it is actually more than 1. So what we are therefore forced to is that one of the elements, say x, one of the elements representatives of orbits has to have stabilizer to be of order 2. Otherwise, we can't have this inequality. So in order to respect this inequality, one has to have size of stabilizer of one of the orbit representatives to be equal to 2. What does it mean? It means that edges are there. So 2 corresponds to edges. So x here therefore is corresponding to poles which are coming from edges. So x corresponds to poles coming from edges. But we don't need all this to proceed. I am just making a side remark. And what are other possibilities? Other possibilities are precisely these. So I have written all possibilities. So stabilizer 2, then next element, other orbit has stabilizer size 2, and then other one has stabilizer size r for some r, and similarly 3, 3, 5, 3, 4, 5, like that. Okay, consider this situation. When n is 3, stabilizer of x is of size 2, stabilizer of y is also of size 2, and stabilizer of z is of size, say, r. Then what happens? So if r is equal to 2, r is this. So stabilizer of z is also of size 2. Then in one of the earlier formulas, if we put all these values, which formula? This one. So here everything is 2, 2, 2. So 1 by 2 plus 1 by 2 plus 1 by 2 is 1 plus 2 by mod g, and that gives us that order of g is 4. Now as you know, there are only two groups of order 4. One is cyclic group and another one is Klein's 4 group. Cyclic group is certainly there in SO3. What about Klein's 4 group? Klein's 4 group is also there in SO3. How to see that? And that's quite interesting description. You think of a sphere and you think of 3 axes, x-axis, y-axis and z-axis. So that forms a system, that forms an orthonormal system, and consider with x-axis the minus direction as well, with z-axis minus direction as well, and with y-axis also minus directions. So the 6, you just imagine the three axes intersecting at the center, intersecting at the origin. Now what is the symmetry? What are the symmetries of this? So you consider rotation by 180 degree for each of them. So you imagine rotations by 180 degree about the standard x, y and z axis. So then these rotations along with identity, they form a subgroup of SO3 which is isomorphic to V4. In fact, here you can think in terms of quaternions because rotations will be in terms of ijk, and you can think of I, j, I inverse. These kind of things you can think of, and ij, I inverse is what? Is minus j. So it's the rotation by 180 degree. So these kind of things you can think of. So we have obtained that V4 is also a subgroup of SO3. So here R was greater than or equal to 2. So this was R is equal to 2 case. So if R is greater than or equal to 3, then what happens? So that's where we make use of the fact that G is an isometry. G meaning the elements, if I pick an element of my group, then it is an isometry, that is it keeps the distances preserved. So first thing to observe is that if R is greater than or equal to 3, then size of G is twice of R. How do we get it? Again, from one of the formulas, this one, I obtain that. Just put 1 by 2, 1 by 2 and 1 by R. So you will get that G is of order 2R. And I pick this stabilizer. Now this stabilizer obviously fixes the pole Z. Stabilizer of the pole Z of course has to fix the pole Z, and of course the antipodal pole minus Z also has to be fixed by this. Therefore, this is actually a cyclic group of order R, and stabilizer can be written as 1G, G square and so on. And now this stabilizer, this cyclic group acts on other poles. So I just take one other pole, say x. So I consider x, gx, g square x and g to the power r minus 1x. I claim that all these are distinct. If that were not the case, some smaller power of g would be fixing x, and some smaller power which is different from 0. So for some I which is different from j, I would be getting that g I to the power I minus j fixes x. But elements of this, all these powers they are allowed to fix only z and minus z, and certainly x is not z and x is not minus z, and therefore these are all distinct. And now we see the distance preserving observation. So x and gx, the difference of x and gx distance on the sphere, the Euclidean distance, these are all Euclidean distances. So Euclidean distance is same as gx and g square x. So I have transformed this and this both by g and so on. So like this I have. And I do the same thing with z. The point is g to the power I, z is z. So everywhere I am having z, z, z. So this kind of picture is what I am getting. So what is that? That means x, gx, g square x, g to the power r minus 1x, they are equidistant from z. And among themselves also they are equidistant. So the picture is something like there is a north pole, something like this, z, and each, so you can imagine z like north pole and g to the power ix, these are equidistant points. on equator. You can think of it like this. So that gives important clue about how the poles are configured. These are coplanar. As I said, they are on the equator and their plane is orthogonal to what joins north pole with south pole, z with minus z. And therefore, these are forming vertices of regular argon. And when I observe rotations of this regular argon, I realize that these rotations are actually isomorphic to G. There is some small calculation which is involved there, a small argument which is involved there, and using that, essentially what is happening is that G is nothing but the regular argon which is made by x, gx, g square x and so on, g to the power r minus 1x. These distinct points, they make regular argon, and that is how G becomes isomorphic to dr. In other cases as well, we have similar kind of analysis. Let us take this analysis where I had subcase 2, in which case stabilizer was 2, this stabilizer was 3 sized, this was size 3. So again I can use one of the earlier formulas. Which one? This formula. So I had 2, 2, 3. So let us see. 1 plus twice of order of G is 1 divided by 2 plus 1 divided by 3 plus 1 divided by 4. So if I do this calculation, what do I get here? I get 12 and then 6 plus 4 plus 3, which is 13 by 12, and then I subtract it. So 2 divided by this is 13 by 12 minus 1, which is so which gives me that, so this is 1 divided by 12, so size of G is 24. And similarly in the previous case, size of G is 12. So I have actually done the calculation for next case. So in the previous case also, in the similar fashion, size of group is 12. And because of orbit stabilizer formula, we get that stabilizer of Z is having this relation, orbit of Z size is same as 12 divided by size of stabilizer, which is so, and this ratio is 4 because stabilizer Z is 3. So 12 divided by 3 is 4. Now what do? We pick an element which is there in the orbit of Z, an element which is different from Z and minus Z. We can do that because orbit of Z has 4 elements. So one is Z, other is minus Z, and 2 more elements. So I can pick, say, W. And now I do some jugglery with all this, and if the stabilizer of Z is, see, stabilizer of Z is cyclic, it has 3 elements, so let us call it 1 G, G square, and then I look at the effect of the size of stabilizer of Z on this element W on the orbit, and conclude that there are 3 distinct elements, W, GW and G square W. And using previous kind of analysis, it's not very difficult for me to conclude similar kind of argument using the fact that G is distance preserving, that Z and W, GW, G square W, they actually form a regular tetrahedron. So since they form a regular tetrahedron, I can have a homomorphism from the finite group G that is given to me to the group of, this is group of rotations of tetrahedron. I can have that. And again, it's not very difficult for me to conclude that size of G is A4, because you can make count of elements and all that. So the group in this case is A4. Again, when stabilizer is of size 4, I can do similar kind of analysis, exactly same kind of analysis, and I can conclude that G is S4. And similarly, when stabilizer is of size 5, I can conclude that G is actually a group of icosahedron which is A5. And then all the cases are finished. So I have this case of A5 which is finished. Before that I had case of cube which is finished, and before that I had case of tetrahedron which is also finished. So we are therefore back to the original statement, which is that these are all subgroups of SO3. What goes there? You carefully examine what are poles, how stabilizers of other poles are acting on those poles, and that would eventually lead either to platonic solids or to a polygon which is right there on the equator, or on a situation, it's a Klein's 4 group situation where you have the 3 axes, x, y, z axis, which are inscribed inside a sphere. So that's how we prove that SO3 has finitely many groups, and those groups are what I have already mentioned to you in this lecture. So this was all about our group action, and how group action is useful for understanding subgroups of SO3. And crucial thing, as has been, is the distribution, analysis of distribution of poles on sphere and their orbits under G action. So as you have seen throughout this course, throughout all these lectures, group action is quite an important thing. You can use group action to understand certain symmetries, you can use it to understand certain puzzles, certain games, and also while doing more mathematical, while exploring other aspects of mathematics, other branches of mathematics such as representation theory, matrices and all that, also our group actions are important, they are quite inevitable. To end this course, I would just mention to you certain open problems in group theory. So those open problems are, most of the open problems are difficult to state, they need much more mathematics than what has been covered in these courses, in this lecture series, but nevertheless I managed to find certain problems which are, which can be understood in terms of the parlance, in terms of the terminology that we have used in this lecture series, and I would mention it to you. And all these problems I have taken from what is called Kurovka's notebook. So Kurovka's notebook is maintained by Kukro and Nazirov. These are two renowned group theorists. They work at this place in Novosibirsk, Russia, Sobolev Institute of Mathematics, and this Kurovka notebook is currently in its 19th edition, 2018. So latest one just came out a couple of days ago. So I am just mentioning few problems which are open problems. So even basic group theory that we discussed during these courses has makes us capable to understand at least some statements, if not proofs. There are many problems in this book for which you need much more background, and those problems may need lot of probably in some cases geometry, lot of algebra, but these are very straight to understand problems. So I am mentioning these. So this is problem 19.11 from Kurovka's notebook, which says that can you estimate conjugacy class size for, can you estimate the number of conjugacy classes for finite groups? So it says that can we actually express number of conjugacy classes as some constant times log of 2. Sounds quite interesting. We are counting conjugacy classes, how many conjugacy classes are there in terms of log of group size. Looks interesting. So this problem is attributed to E. Bertram. Another problem, problem number 19.30, and it is in terms of complex characters. Remember, in one of the earlier lectures we have seen what complex characters are. So an element, a finite group, is said to be vanishing if chi g is 0. What is chi g? So it's chi g is 0 for some irreducible complex character. So if on G some irreducible character vanishes, then you call this element to be vanishing. Now the question is, if you have a finite group and then you have another finite simple group, and suppose if they have equal orders and same set of, so if the finite simple group and finite group, they have same order and the same set of orders of vanishing elements. So you take vanishing elements and the order of vanishing elements. Suppose the order of vanishing elements, these two sets are same. Can we actually conclude that these two groups are isomorphic? Sounds quite interesting. Another one, which is due to Huysmans, which says that you take a finite group of order n and you factorize this order. So a1, a2, ak, these are this integer factorization. So is it true that for every factorization you can break, you can find partitions, you can find subsets a1, a2, ak of the group such that a1 has size a1, a2 has size a2, ak has size ak, and every element of G can be obtained as some element of a1 times some element of a2 times some element of ak. So again, it sounds quite an interesting problem. Last problem, which is due to none other but the famous Fields medalist, the famous mathematician of our times, Jean-Pierre Serre, and the problem is very simple. It asks about infinite simple subgroups of SL2Q. So SL is collection of, SL2 is collection of 2 by 2 matrices, and here over rationals. So 2 by 2 matrices of rationals which have determinant 1. In that group, can you find infinite simple subgroup? And it's quite surprising that such problems are still unknown. So whether such statements are true or not is still unknown. So through this I just gave you a glimpse, and each year in this Kurovka's book, Kurovka's notebook, they keep adding problems. 2000, it's a 19th edition. These are actually the latest editions. The latest edition they have added some 111 problems, and overall there are thousands of problems in Kurovka's book which are still open. They also keep updating what problems have been solved, or if some progress is there, what is the status, current status of that. So it would be quite interesting if someone can even comment, even small comment about these or some examples. That would be quite worth it. So with all this, I am stopping my lecture series. Purpose of all this was to make you appreciate what groups are. Although in usual courses, in many regular group theory courses, you get to know of various aspects of group theory. You get to learn what Cauchy theorem is, what Sylow subgroups are, and then there are many other aspects, how many groups, how many elements of which order and all that. But we fail to understand the connection of group theory with various real life problems, and through this lecture series I just wanted to bring that out, so that with the small definitions, with not much baggage in group theory, we could enjoy, we could appreciate why groups should be there, and right from those basic definitions we could also see all these hard problems, all these open problems which are there in Kurovka's notebook. there is not much that I would say in this course now. I hope you enjoyed all this lecture series. If you had any query, you can write to me, you can ask me through online interface, or whenever I get live on YouTube, you are always welcome to ask all the questions. Thank you very much. Thank you for being for all these lectures throughout. Thank you.